So today we're going to talk about metabolism, chapter 27, and different aspects of it. So we'll start out with nutrition. So really, nutrition is how do you obtain nutrients. And nutrients need a definition. So nutrient is something that you need to sustain life. They are the building blocks of metabolism for synthesis of new molecules. We get our nutrients through ingesting them, usually through food, although water is considered a nutrient. Vitamins, minerals, and organic molecules are what most of them are. We're going to see that concentrations of nutrients go way up when you've eaten, and they go way down as they get used, and you're fasting. So how these things are maintained at a decent level is a major topic of this, how we regulate this endocrinely. So there's a couple of different types of nutrients. There's the macronutrients. These are the things that we need lots of, that we need to ingest on a regular basis, and we're using up at a fairly quick rate. And these are really the carbohydrates, proteins, and fats, the lipids. These are the main things. We use them mostly for energy, for making ATP. We also use them for structural materials and building cellular components. The micronutrients we don't need as much of. So these are the vitamins and minerals. We need to have them. We can get them from a number of different sources, but we don't need them in large quantities. As a matter of fact, some of them in large quantities can have a negative effect. Now, we also talk about nutrients as being essential nutrients or non-essential nutrients. So essential nutrients, the only way we get them is from an outside source, that they have to be consumed as that nutrient, because we don't have the capability of changing some other molecule into them. The non-essential, actually, you can. There's biochemical processes within the body that can modify things. So, for instance, there are some amino acids that we need to consume. They're called the essential amino acids. But the vast majority of amino acids we can create as we need them. And the non-essential amino acids. Both of them would be macronutrients. So because of this, they've done studies as to how much do we need of each thing. And this is the recommended daily allowances. You'll see it on food packaging that the percentage of the recommended daily allowance will be on there of macro and micronutrients. So, and vitamins, so it's like, it'll say that it's 10% of your sodium intake, and etc. So those things are really a guide to making sure that you're not deficient in any of these nutrients. Now, one of the problems is averages, that each individual needs different amounts. So this is not hard and fast, but just basically a general rule of thumb. Different people process different nutrients differently. That's part of the genetic makeup. Different people are different sizes and need different amounts of things. You know, some people have a faster metabolic rate than others, etc. So there's a lot of individuality, but within a general population, these are good general rules of thumb. So the macronutrients we mostly use to make ATP. They are sources of energy for the most part. And so we measure that energy in calories. And a calorie is the amount of heat required to raise the temperature of 1 gram of water by 1 degrees centigrade. And that is a small c calorie. That is the calorie used in physics. The calorie used in nutrition is actually a kilocalorie, which is usually written with a capital C. So a kilocalorie is 1,000 calories. So if you are eating 2,000 calories a day with a capital C, what you're really taking in is 2 million small c calories, so that you could raise the temperature of 2 million grams of water by 1 degree centigrade. Whatever. Just realize that the calorie of a physicist and the calorie of a nutritionist are significantly different. So these macronutrients, really there's carbohydrates, lipids, and proteins, so we'll look at each one of them separately. So carbs, carbohydrate, all have the formula C to the X, or C subscript X, H2X, O, X. So it's really H2O is water, hydrate, and C is carbon, so carbohydrate. So if we look at something like glucose, it's C6H12O6. If we look at ribose, it's C5H10O5. Carbohydrate, carbon and water. Usually these things are found in a ring, so and we call this ring a sugar, a monosaccharide. We can join two of these rings together to make a disaccharide, or make big chains of these things called polysaccharides. So the things where we get these from is the carbohydrates in our food. They are always present in our food, but not usually as monosaccharides. Usually more as polysaccharides, long chains, big macromolecules. If the big macromolecule is digestible, meaning that we can break it down into eventually the monosaccharides, then we call it a starch. If we can't break it down, we call it fiber. So cellulose, for instance, is a polysaccharide. It's a long chain of sugars, of monosaccharides, but we can't digest it, so we call it fiber, and it's what actually gives bulk to your poop. Sugars are much smaller. There's the disaccharides and the monosaccharides. So when we talk about sucrose or lactose, those are disaccharides. There's two monosaccharide rings joined together. The monosaccharides are glucose, fructose, and galactose. as far as those things are all concerned for energy production, they all are C6H12O6. The ribose and deoxyribose are also monosaccharides, but we don't use them for energy. We use them for making nucleic acids. So glucose, fructose, and galactose are the monosaccharides, and these are the things that we actually absorb in our digestive system. We might eat a disaccharide like sucrose, but we break it down, we digest it into glucose and fructose, and that's what gets absorbed into our bodies. Lactose are found in milk, sugars found in milk, maltose found in most cereals. That's why you have malted cereal. There are other sugars like dextrose and things like that are slightly more complicated. They might be 3 or 4 monosaccharides instead of the disaccharide, but they break down just the same. They are not huge polysaccharides. Starches, on the other hand, are long, polymeric, very large molecules, but they are really chains of monosaccharides. So we find them in a lot of plant foods, but we also find them in animal foods. For instance, turkey breast is full of glycogen, which is a polysaccharide that we can digest and we can use. And like I said before, the difference between starch and fiber is whether we have the enzymatic capability of digesting it, of chemically digesting it, breaking it down into its simpler forms that we can absorb. Fiber cannot be. Now, fiber is still an important part of our diet because it really helps with the functioning of the alimentary tract, with the digestive system. So it's important, but we just don't gain any energy from it, and it never enters our body. It stays in the lumen of the alimentary canal. There are some animals that have the capability of digesting what we would call fiber, cellulose being particularly it, and they can, they tend to be the herbivores. So they are things like cattle and goats. Beavers eat wood, which is all cellulose. So there's lots of animals that actually can break down these substances, but they have digestive tracts that are specific to being able to do that, and they produce the enzymes that can do that. Now, a lot of it is fermented and broken down by the flora and fauna in their digestive tracts, so that's why they have multiple stomachs and the ability to break down this stuff, but we can't. We use carbohydrates to make ATP. It's the primary energy supplying nutrient. The main monosaccharide that we actually oxidize to make ATP is called glucose, and that's why we measure blood glucose levels, because that's what we circulate around. That's the fuel for cellular metabolism. Now, we don't necessarily have to eat glucose. we can make glucose. In the liver, in the kidneys, we can do something called gluconeogenesis. We can make new glucose from things that aren't glucose. We can take amino acids and turn them into glucose. We can take fats and turn them into glucose. We can take other carbohydrates like fructose and things and turn it into glucose just by rearranging some of the chemical bonds. So we have that capability. Now, glucose is an important fuel for the central nervous system because it's the only fuel the central nervous system will use. Now, if we consume more carbohydrates than we need to supply our ATP, we store that energy in a much more energy-dense form, and these are the lipids. Now, there's 4 categories of lipids. There's triglycerides, phospholipids, steroids, and eicosanoids. Triglycerides are the things that you think of as fat. They have a glycerol backbone and 3 fatty acids coming off them. And fatty acids are just long chains of carbons and hydrogens with 1 oxygen. Now, because these are long chains, carbon-carbon bonds, that's where the energy is stored as carbon-carbon bonds. And so if we have a fatty acid that's, say, 23 carbons long, it holds way more energy, it stores way more energy than a glucose molecule that is only 6 carbons long. And a triglyceride will have 3 fatty acids, so that could be 69 if it's 23. If each fatty acid is 23 carbons, it would be 69 carbons, plus the 3 carbons of the glycerol, we're at 71 carbon-carbon bonds, which is significantly higher than the 6 that you're going to have. So per molecule, there is more energy stored in a triglyceride than just about any other carbohydrate, or just about any other organic molecule. Now, if the carbon-carbon bonds, if there's a bond between each carbon, and as you know, carbon will form 4 bonds. So in the chain, each carbon is bound to the carbon in front of it and the carbon behind. So there's 2 of the 4 bonds. The other 2 bonds are filled with hydrogen. If every carbon has 2 hydrogens, then we call that fat saturated. It has got the maximum amount of hydrogen available. If some of the carbons actually have double bonds between them, so if carbon 6 is double bonded to carbon 7, carbon 6 is also bonded to carbon 5 and double bonded to carbon 7, and carbon 7 is double bonded to carbon 6 and a single bond to carbon 8, there's only room on 6 and 7 for 1 hydrogen. So we call that unsaturated. So if there's a double bond in the fatty acid, it is an unsaturated fatty acid. If there's more than 1 double bond, it's polyunsaturated. So those are the kind of the 3 categories of triglycerides. And the main point of triglycerides is to store energy. So the saturated, no double bonds. A saturated fatty acid or a saturated triglyceride is solid at room temperature. So this is meat fat, these are the dairy fats, coconut oil, palm oil are saturated fats. Now, even though coconut oil, it says it's solid at room temperature, it doesn't take very much above room temperature to become oily, but nevertheless, those are the saturated fats. The unsaturated fats have at least one double bond. They tend to be liquid at room temperature. So these are the oils that are found in nuts, canola, olive, sunflower, almond, like all of those oils are unsaturated. So polyunsaturated would be things like corn oil, soybean oil. And so you really can't tell the difference unless you read the label. Now, cholesterol is a type of lipid as well. Cholesterol is a very important thing for us. It has a bad reputation because most of us have more cholesterol than we need, but we do need some. It is a precursor for all the steroid hormones, so it's an important thing for that. Vitamin D is a cholesterol derivative. Sunlight on the skin converts cholesterol into a inactive form of vitamin D, which then gets activated by the kidneys. BIOL salts have cholesterol in them. The plasma membranes of every cell remain pliable because of cholesterol. It's really important. Now, some cholesterol comes from the diet. Most cholesterol is actually synthesized in the liver. It's one of the main functions of liver is to make cholesterol as needed. If your cholesterol levels are high, it's probably got more to do with how much you're making in your liver than how much you are actually eating. Stress causes the release of cortisol. Cortisol is a steroid hormone made from cholesterol. So when you're stressed, your liver puts out more cholesterol because it's going to be needed or to make cortisol. Most of the hormones that are made from cholesterol, which is a steroid, has sterol in it. So cholesterol, chole means bile, steroid, so it's the bile steroid, cholesterol. Cortisol, aldosterone, testosterone, like those are all have the ster in the word, are made from cholesterol. Proteins are long chains of amino acids. There are 20 amino acids. We need them to make new proteins, but we can also oxidize them for ATP. Now, there are 20 amino acids that are used by the body. 8 of them are essential we need to get from our diet. 12 of them we can make from other things. We can make them from glucose, we can make them from fat, we can make them from other amino acids. We change the R group on the amino acid and we can synthesize them. But 8 of them we can't synthesize. They have to come from the diet. So if the protein that we're eating contains all the essential amino acids, it's called a complete protein. It doesn't matter about the non-essential amino acids. So you don't have to have them all because we can make them. A complete protein has all the essential amino acids. Now, for the most part, it's animal proteins to be complete. So we don't tend to get them from vegetable proteins. The exception, as far as I know, is quinoa. So there are other plant sources of complete proteins. I think buckwheat falls into that category, although it's debated. Now, some authors say that there are 9 essential amino acids. Most say 8. I've actually seen some authors cite 6. Again, this is all just, you would think that this would be a settled argument. I think it's got to do more with the ease of creating these. So your textbook says 8, we will stick with 8. So for people that are on vegan diets, it's something that really matters. Animal proteins, eggs, milk, they tend to be complete. So usually what people have to do if they're eating incomplete proteins is combine them. So rice and beans together will give you all the essential amino acids, because the essential amino acids missing from beans and the legumes is in the rice, and the ones missing from the rice is in the beans. So the Jamaicans are onto something with rice and peas. So this has to be something that's taken into consideration when doing nutritional analysis. Now, the other thing is that we don't store amino acids as amino acids, so they have to be regularly supplied. Now, we recycle them. If we are breaking down proteins that are no longer useful, we will reuse those amino acids, but that's not the same as storing them. It's got more to do with recycling. It's unlike energy, it can be stored as fat. Amino acids are either used, or if there's excesses, they are just peed away. So you have to, if you're vegetarian, especially vegan, you have to be very cognizant of these things, and we'll just kind of leave it at that. Now, the other thing that amino acids supply for us is nitrogen, because the amine end of an amino acid is NH2. So there's a need for nitrogen in the body. So DNA and RNA specifically have nitrogen, and to synthesize these things we need the nitrogen, and it mostly comes from the proteins. So usually there is an equilibrium, because if you eat too much, you pee away the excess. That's what urea is, and creatinine. And so we have ways of excreting the excess. So usually there is a balance between intake and loss. And if there's an imbalance, it's usually when there is more taken in than can be lost. We very seldom, especially in the West, have a problem of having a negative balance, at least from nutrition. We can get a negative balance from blood loss, because we can lose it by hemorrhaging. Sometimes we have a positive balance when there's growth or tissue repair, or a new person being supplied. So we want a positive balance where we're taking in more than we're losing, because we use it up. But even then, there's an equilibrium in that.